Hi, welcome to the screencast. This one is going to be about potential. No, it's not, because I forgot to do that. Hi, welcome to the screencast. This one is going to be about potential. Ultimately, we're going to be talking about membrane potential, but first, just to define potential in general, as it says right there, that is, an electrical potential is a separation of charge. So if you have opposite charges, negative and positive, separated from one another, they are going to be attracted to each other. This, as it says right here, represents a kind of potential energy because you have two charged particles that want to move. There is a force drawing the two of them together. If these two particles are separated by a membrane and they are able to feel attractive forces through the membrane, so there has to be a channel or a pore of some sort involved, then we call that the membrane potential. And what we're going to get to ultimately is the membrane potential when the cell is at rest or when it's not being stimulated, in the case of muscles or neurons. So it's going to be the resting membrane potential. But I want you to understand all of the factors that go into it rather than giving you a number to memorize, which doesn't mean anything. So the first thing we have to discuss or talk about first is something that we just recently talked about, the sodium-potassium pump. Again, I can't overemphasize how important it is to remember that every cell in the body has the sodium-potassium pump, or the sodium-potassium ATPase, which, as it says right here, is going to pump 3 sodium out of the cell and 2 potassium back into the cell, giving you opposing gradients of sodium and potassium. So I'm going to attempt to diagram membrane potential one thing at a time slowly, so that you have the opportunity to understand this as we're going over it. So let's just draw a pump here. I don't really know exactly what the pump is going to look like. We'll give it a little opening on one side and an opening on the other side, and it is pumping. Oh, what a horrible drawing. There we go. So what is going out? Sodium is going out, so that is Na, which we'll just draw as a bunch of little positives, well, red positives, right? And then potassium, also positively charged, that's coming in. So there's potassium being pumped into the cell, sodium being pumped out of the cell. So we're going to put a whole lot of potassium in here. And just a little bit more sodium out here, all of these little positive charges. Then you also have inside the cell, let me get a different color, how about yellow, anions, and I'm just going to draw these as an A. This is mostly proteins. And then on the outside of the cell, you'll see when we get to the book's drawing, the most prominent anion, negatively charged ion outside the cell is chlorine. So starting at baseline, what you have then is these two opposing gradients with lots of potassium inside the cell, lots of sodium outside the cell, but they're balanced by negatively charged proteins inside the cell and negatively charged chloride ions outside of the cell. So there isn't a charge imbalance on either side of the cell. There's just these opposing gradients. So in the book, it would look like this. Ignore the things lined up at the membrane for now, but just notice that you've got positive charges inside the cell offset by negative charges, and positive charges outside the cell offset by negative charges. So there is charge neutrality in either compartment, and an equal distribution of charge overall on either side of the membrane. What we are going to end up with is not a difference in the number of charges, but simply how those charges are arranged. So it is a very local phenomenon. So we're going to go back to my original picture here, and then let me just make this a little wider. Over here, we are going to put a channel. So imagine this is like a circular protein. I'm a horrible drawer. That's supposed to be a channel, but I'll just get rid of those two things. And oh, that's not what I meant to do. It erased the whole thing. All right, we'll leave the membrane there. Imagine that this is empty right here so that stuff can pass through it. This channel is primarily permeable to potassium. And it's always open, so it is called a potassium leak channel. So what's going to happen is that potassium is going to leave here. So we'll just draw some positive charges. Technically speaking, other ions can pass through this channel, but it is more permeable to potassium than other ions. So it is mostly the effect of potassium leaving the cell that is setting up our resting membrane potential. So you have this steady outflux of ions here. Your intracellular concentration of potassium is going to remain high because the pump keeps pumping potassium back in. So you're always going to have or maintain these two opposing gradients. So what happens as potassium tries to leave, right, the negatively charged anions want to follow it out of the cell because opposite charges are attracted to each other. But they're really big proteins and they're negatively charged, so they can't make it through a channel that is designed or intended to let positive charges through it. So what happens is now you can see there's some positive charge lined up on the outside of the cell as potassium is leaving, and some negative charges lined up on the inside of the cell. Because this is an open channel and potassium can pass through it, right? Potassium can still feel the electrical attraction to the anions, and the anions can still feel electrical attraction to the potassium. So what happens as more and more potassium leaks out, whoops, wrong color, but you get the idea, more and more potassium leaks out, you get more charges separated across the membrane, or a larger potential. And at some point, the strength of the concentration gradient that is forcing potassium out is going to equal the electrical gradient, or the electrical force attraction that potassium feels for all the anions that it left behind. And then what's going to happen is for every potassium that goes out, another potassium is going to come back in. So you're going to get to a resting state where potassium ions are going out and coming back in, and lined up, some potassium ions, some sodium ions lined up on the outside of the membrane, being attracted to the anions that are lined up on the inside of the membrane. So, whoops, I skipped ahead on you guys. This then is what it looks like when all of this stuff happens. I'm not going to go back over this again, but this is all of the text that gets you to this figure here. And the way the book illustrates it, it looks like this, but I wanted to go step by step so you could see how everything happens, right? But lots of potassium inside the cell, lots of sodium outside the cell. Potassium leaves because it is just traveling down its concentration gradient. That is what it wants to do. So as it leaves through this channel that is always open, anions try and follow it. They end up trapped on the inside of the membrane. And because electrical forces can be felt through this channel, not through the phospholipid bilayer, because that's lipid insulation, so like this sodium here is not feeling a direct attraction to this anion here through the phospholipid bilayer. There has to be an open channel that electrical forces can be felt through. So potassium leaves, anions try and follow it. They end up stuck on the inside of the membrane, and again, because those forces can be felt through this channel, positive charges line up near these leak channels, which are everywhere, not everywhere, but regularly distributed across the surface of the membrane, or across the whole cell. So throughout the cell membrane, there are these channels scattered around, so you get positive charges lined up on the outside, negative charges lined up on the inside, and when the force of the concentration gradient pushing potassium out equals the force of its electrical attraction to the anions, you get this steady state, and that is your resting membrane potential. So it's the potential at which every time a potassium leaves, another one gets pulled back in because it's attracted to these anions. So the big important conclusion then is that, because what I just explained happens in pretty much every cell of your body, there might be an exception out there, but I am not aware of it. Every cell in your body then has a resting membrane potential that is slightly negative if you are comparing the inside relative to the outside. So we always, when we refer to the membrane potential, we're putting our voltmeter on the inside of a cell and measuring the separation of charge inside relative to outside. So every cell of your body has some negative charges lined up on the inside of the membrane, some positive charges lined up on the outside of the membrane, and they are electrically attracted to one another, and that is what develops or causes this resting membrane potential to develop. Later on, when we do muscles and neurons, we are going to add other channels in addition to this one here that is going to let sodium flow in, or maybe even more potassium flow out, and that is going to result in changes to the membrane potential. So there are going to be all sorts of fun little tricks that your cells do with their membrane potentials, and this is what is meant by like neural signals or excitability. It's electrical excitability. And I'm going to stop there and make a separate screencast for the end of the chapter cell cycle stuff.